In this video, we'll take another look at KVL, Kirchhoff's voltage law. We've applied it according to the loop rule, which says that the change in energy throughout the system must equal zero. That means any energy increase must be equal to the energy decrease. We applied that in terms of energy per unit charge, which gave us the sum of the voltage increases around a closed loop must equal to the sum of the voltage decreases around the closed loop. We said that voltage increased in the direction of the EMF arrow, that was our EMF rule, and that voltage decreases in the direction of the current, it's going to decrease across the resistor. So now we'll take a look at KVL. Instead of according to conservation of energy, we'll use the concept of the fact that we know that electrical force is a conservative force, though it's path independent. So the potential differences in a circuit, the potential between any 2 points in the circuit, must be the same regardless of which path we follow. So that's what we mean by path independence. So any path we take from node B to get to node A in this circuit must give us the same potential difference. So if we look at this circuit, if we take a path going clockwise and we start at VB, we'll say VB, we'll use our resistance rule in the direction of the current through the resistor. So we have VB minus IR, and then we get to VA. So that's equal to VA. So we could rearrange that and say the potential difference, VB minus VA, then is equal to IR. And that's we got from our clockwise path. If we go on our counterclockwise path, if we start at VB, now we're going to be going downward through this resistor, but we're going to be going in the opposite direction of the current. So that's going to give us a plus IR, because we know if the current is flowing upward, the potential difference across this little resistor is going to be in this direction. So we have our VB plus IR going in the opposite direction of the EMF arrow, so it'll be minus our EMF, and then we get to VA, so that's equal to VA. So if we rearrange our equation, we get VB minus VA is equal to our EMF minus our current times little r, so minus our IR. So we end up with our two equations. We can set these two equations equal to each other since VB minus VA is EMF minus IR. It's also equal to IR. Then our EMF minus IR equals IR. And we solve for our current is equal to the EMF divided by the sum of the resistances, just like we did when we solved for it using the loop rule. We also see that we have a volts per ohm, so we have the correct units in our check. And we also can think of this, well, we have a series loop. The sum of our resistances is R plus little r plus R. So we have, by Ohm's law, the total voltage across the loop divided by the total resistance in the loop gives us our current. So we have a third way with this to solve for this, and that's a KVL looking at potential differences throughout the circuit. So now we can define a potential at a given point, VB. That potential at that point, VB, is relative to a zero somewhere. We haven't defined where that zero is, but we said we know that that potential at VA is relative to the same zero. That's why we can say VB minus VA and look at just a nodal voltage instead of a potential difference across an element or part of a circuit. So when we look at this, we can then solve for, since our I is equal to E over R plus R, if we plug that current back into our equation 2 here, we get our VB minus VA is equal to the total voltage times the resistance R here divided by the sum of the resistance. That gives us our voltage division. So the voltage across the larger resistor, or whichever resistor, the voltage across the resistor is going to be equal to the total, the voltage across resistors in series is going to be equal to that resistor divided by the total resistance in the series circuit multiplied by the EMF, or the voltage across that. As a further example, again, we can do voltage division when resistors are in series. So all these elements, so our potential difference from VB to VA, VB minus VA is equal to the EMF. So we could replace here, noting that our EMF is equal to VB minus VA. That's the potential difference across all the sum of all these three resistors. So V1 then is going to be equal to that voltage times the 10 ohms divided by the sum of all the resistances. V2 is going to be equal to the total voltage times the 20 ohms divided by the sum of all the resistances. And similarly for V3. So V3, that 30 ohms is our R3. So that's voltage division. We can use that as well as a way to analyze. We have to make sure that in fact our resistors are in series and we're using the voltage across the sum of all of the series resistances. So let's look again at our ideal battery. We said we can model an ideal, a real battery as an ideal EMF, which we have here modeled as our battery with the EMF arrow, in series with a resistor, where that series resistor represents the energy loss that the battery experiences when it's trying to deliver power to the rest of the circuit. So when we talk about the energy loss, it's thermal energy that that the battery consumes in trying to deliver the energy. So whether we put the resistor at the positive side of the EMF terminal or at the negative side of the EMF terminal doesn't really matter. If we're just trying to solve for current, then it doesn't matter where any of the series elements are, we can move the elements around. And that's, we're mathematically modeling. That's what we're doing with these circuits. So just like when we are adding, we can move the variables around in our circuit, and that doesn't change the total result. So if we look at the potential difference here, VB minus VA, in order to find that, we can start at VB plus IR in the opposite direction of the EMF arrow, minus E, or EMF, in the opposite direction of the EMF arrow. Plus IR was the opposite direction of the current. So that's equal to VA. So our VB minus VA is not the EMF, it's the EMF minus IR. So the more current that the EMF device has to provide, the less efficient it's going to be. It's going to have more energy loss. If it's providing zero current, if this is an open circuit, our resistance is infinity, then the potential difference across the EMF will be the same as the EMF itself. If as we increase the current, that potential difference is going to decrease. And we can model that, we can look at that linearly if we have our reference potential here at VA. As we go across the EMF device, we're increasing, we'll model that as increasing linearly as we go through the EMF device till we get at the other side of the EMF device, and then our potential will be at E, whatever our EMF is. And it will not change, and this little equal potential here will have no change in voltage until we get to the resistor. Across the resistor, internal to the EMF, we have a potential decrease. That potential decrease amount is I times R. The R we'll consider a constant. The I will vary depending upon our load resistor over here. And again, across this part of the circuit, that's an equal potential. We have no change in voltage. As we go through the load resistance, we again decrease till we get back to our reference potential VA, because this again is an equal potential. All right, so if we look then at the voltage delivered to the circuit in this example, our VB minus VA, that's our EMF times R, the load resistance R divided by the internal resistance plus our load resistance. If we plug in our numbers, we end up with an EMF of 12 volts, delivering a voltage to the rest of the circuit of only 8 volts. Or we can view that as in pumping charge, the battery does a work of 12 joules per coulomb, or 12 volts, but because of the internal resistance, only 8 joules per coulomb, or 8 volts, is delivered to the circuit. So if we look at the efficiency of this device, the energy delivered divided by the energy supplied, we have 8 over 12 times 100%, so it's 67% efficient. Let's look at power as well when we look at potential and EMF. Power is the net rate of energy transfer. from the EMS device to the charge carriers in this case would be just the current times that EMF, our IV, where our V is the EMF. That's going to be power delivered when we have the current flowing in the direction of the EMF arrow. The net rate of energy turned into heat in the EMF device, well, we can use our I squared R. That's going to be the internal EMF dissipation rate. And the rate of energy delivered to the load, we can use our I times VBA, since that's the voltage across the load. Our VBA, of course, is our EMF minus IR, so our power delivered to the load is our IE minus I squared R, or it's equal to the power of the EMF minus the power of the resistance, and we have conservation of power in our loop. So again, power delivered to the load is generated by the EMF less than that dissipated in the internal resistance. So we can look at our circuit in terms of power or in terms of voltage. Let's look at this example. We want to find the power delivered to the two load resistors and the power supplied by the two EMF devices, and the power absorbed by the EMF devices that will be absorbed in these internal resistances of the EMF devices. So if we label with variables, we want to find the power of the 3 ohm resistors and the 7 ohm resistor, and then from supplied by the EMF devices. So our load resistors are always going to absorb power. Any resistor is always going to absorb power. An EMF device can absorb or deliver power. It depends on the direction of the positive current relative to the EMF arrow. If our positive current is pointing in the same direction as the EMF arrow, or pointing in the direction of potential increase, then that EMF device or that battery is going to supply power. If our positive current is flowing in the opposite direction of an EMF arrow, or flowing in the direction of potential decrease through an EMF device, then that EMF device is going to absorb power. So if we want to find these powers, we can use our I squared R for resistors, or I times V, or the voltage, the EMF, for our EMF devices. So we need to find the current. We can use our loop rule to find the current. If we use our loop rule, we can start at C and end at C. So we have 12 minus I times 2 minus I times 3 minus I times 4. Opposite direction, potential decrease, so we have a minus 4 and then our minus I times 7. We can solve. We have the difference now in the EMFs in the direction of the current divided by our total resistance, and we get 0.5 amps. We can plug that into our equations that we came up with that we knew we were going to look for. So we needed the current. We can then solve for our power. And we note that our 4-volt battery, which has less voltage than our 12-volt battery, is absorbing power as they're in series. We should have this conservation of power, so it should be true then that the power supplied is equal to the power absorbed. So that's always a good check. We will check that against supplying power. We solved that EMF devices were supplying power. So a negative supplied power is the same as absorbing power, but we'll still put it on this side of the equation. So we have our 6 minus 2 is equal to our 0.75 plus 1.75, that's our 2.5. And then we have 2.5 plus 0.5 is 3, 4. So we have 4 equals 4, and check, we have conservation of power. So that's it for KVL and series loops. Our next video will be on KCL and parallel circuits with multiple loops.